Okay, hello everyone. I hope everyone can hear me over the internet. So welcome to the solution presentation for NCPC 2022. So as you can see, if you look at the scoreboard, the problem set was slightly easier than the last couple of years. All of the problems were solved before half the contest was finished, and one team solved all the problems before the freeze. But I still think it turned out okay. So I hope you enjoyed the problems. I hope they were fun to solve. So now let's present the solutions. Or first, before doing that, I want to thank everyone who prepared the problems, the task authors and the test solvers. So next. And they are Per Austin, Atle van Franklin, myself, and Johan, and Bergur Snorason. And also thanks to our test solvers, Joachim, Simon, and Björn. So now let's start with the actual solutions. So the first problem, the easiest problem, the most friendly problem that didn't try to trick you and had a bunch of special cases or anything like that is problem C. In problem C, you are given a sequence of lectures. Some of them have coffee machines and some of them don't. You want to drink coffee in as many lectures as possible. But you can bring coffee from the coffee machines, but you can only hold 2 cups at once. So you have to be a bit strategic with how you manage the coffee. So the solution here is quite straightforward. You just want to greedily bring as much coffee as possible, and if you are at a lecture with coffee, you drink that coffee and it gets expended. So you can solve this by iterating from left to right and keeping track of how many coffee cups you are currently holding and what the answer is, and you will update these values accordingly. Yeah, you can keep a variable coffee that stores the number of cups, and another variable answer that is the current answer. And you will set the number of coffee cups to 2 when you encounter a coffee machine. And when you encounter a room that is a coffee-free zone, you should, well, if you don't have any coffee, you can't do anything. You will have to fall asleep and not increase the answer. Otherwise, you will decrease the amount of coffee and increase the answer by 1. So this is the solution, and there aren't really any tricks here. You just implement this. And a lot of people did. The first person did it already after 3 minutes. And this had 100 and... I have swapped the number of accepted and submissions in the slides, but it should be 198 accepted. So that's quite a lot. Okay, let's keep going to the next problem. The next easiest problem is problem D. You are given a radius around the origin, and you should find a point with integer coefficients or integer coordinates that is outside of this circle, but is as close as possible to the origin. So this problem is also kind of the easiest one in a sense. It is the one with the shortest code, but you can also solve it in a more complicated way if you want. So the more complicated solution is to iterate over the x-axis. So you try all of the x coordinates. So this number r is only 1,000,000, so you can afford to try all the x coordinates. But then you need to quickly find the optimal y coordinate for a specific x coordinate. And you can do this with binary search. So you binary search to find the next y coordinate that is outside of the circle. You can also do a bit of math. I mean, this is a circle, so you know kind of where the y coordinate should be. And so that's the complicated way. The easier way to solve this is to do a bit of math in the beginning instead. So we want to find a pair of coordinates x and y such that the squared sum of them is bigger than r squared. Well, this is the same thing as saying that the sum of squares is bigger than or equal to r squared plus 1. So you can't really do anything better than this. And if you just choose xy to be r1, then this is this is optimal. So you can just print R1. I mean, you can just print input, comma 1, and that's the solution. So this was solved after 4 minutes, and 169 accepted. So I saw teams who did both of these solutions, so both of them were definitely coded during the contest. So now let's keep going to the next problem. The next easiest problem turned out to be problem H, which is a bit surprising to me. I expected it to be problem A, but it turned out to be H. So problem H is a little bit of a step up in difficulty. Here we have a sequence of heights, and you should find the highest hill in the sequence of heights. And a hill is defined as first an interval that is weakly increasing, followed by an interval that is weakly decreasing, and the height is, well, the minimum of the differences. So find the highest hill, and here there are a few different approaches that all work. I'm gonna show the one I did that I think is the easiest, but I don't think everyone agrees. So my idea is to find for each height, find the longest downhill slope in both the left and right directions, because once you have done that, you know kind of the height of the hill centered on that height, and so you know all of the heights of all of the hills, and you just pick the maximum of that. So now calculating these, like the longest downhill slope, you have to do it quite quickly. You can't do it in linear time for each height, because then your code will run in quadratic time. So you have to be a bit careful there. But other than that, I think this is the easiest approach. There are also some solutions that rely on the idea that a maximum hill, like a hill that can't be extended to the left or right, is the answer is clearly going to be for one maximal hill that can't be extended, but such maximal hills can't overlap, so they can only be like a linear number of them. So you can check all of them in some way. So there are some solutions that rely on that as well. So yeah, that was problem H. This was solved after 8 minutes. And yeah, this was the third easiest one. I thought that the next one would be the third easiest one. The next one was problem A. So problem A was kind of easy in theory, but unlike the other ones, it wasn't very friendly. It has a lot of special cases, and apparently it is also easy to misunderstand the statement. So during the contest, we got a lot of clarifications. So there was a lot of ways to interpret the statement that we hadn't thought of, but I think we did a decent job of answering them, or I hope we did. But anyway, let's go through the solution. So the first thing we want to do in problem A is this annoying swapping of the scores. We don't know who has what scores. That's really annoying. We need to take care of that first. That's the first thing we need to do. So we need to unswap them so that we know who has what scores. Okay, so let's see what we should do. If Bob is serving, let's say that we swap them, so we know that Bob is the second always. And the serves, they will follow this ABBA pattern, ABBA, 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 ABBA. And you can see that this pattern has length 4, so whether we should swap or not only depends on the remainder of the score mod 4. And here you can see that Bob is serving when the total score is 1 or 2 mod 4. And the total score is just the sum of the two scores. So I mean, you always know that. You can just add them up and take the remainder mod 4. So now you know when Bob is serving, so you can swap them, so you know who has what score at each point in the game. And that's very helpful. So now you just have to find when is such a log invalid. And it turns out that it can be invalid in 2 ways. So a player's score should never decrease. That can't happen in a game. You can't have someone gets a penalty for doing something rude or something like that. So if that happens, then it's an error. And then there are also errors regarding the end of the game. So the game should end when someone reaches 11. And if the game continues after that point, it's also an error. And one way this can happen is if the score ends up being 11-11 at some point. That shouldn't happen. And that's kind of a tricky case. So this is everything you need to know for problem A. And this was solved after 11 minutes. Also over 100 accepted, so quite a lot of people solved it, but also a lot of wrong submissions. Okay, next problem. So the next problem is problem G. Graduation guarantee. This is about an exam. You're writing an exam and you want to get at least K points. You will get +1 if you answer correctly and -1 if you answer incorrectly. But if you don't answer, you will get 0. So this is to discourage guessing. But if we know for each question the probability of guessing correctly, what strategy should you have? Which questions should you answer? What is the maximum probability of getting the required K points? That's this problem. So first of all, when solving this, we need to decide which questions should we answer, which are the best to answer. And here the key idea is to realize that a high probability of getting a question correct is better than a low one. So if we are gonna answer some questions, if we decide, okay, we are gonna answer M of the questions, why not just answer the M biggest ones? That's always gonna be better than not doing that. So this is the main idea for the solution. We sort the list of probabilities, and now we're just gonna try for all M. If we answer the last M questions, what is the probability now of scoring at least K points? So this is more like a math problem, kind of. If we have a bunch of probabilities, what is the probability of getting at least K points if they can be +1 or -1, depending on this probability? And so you want a subset of size something, and you want to count the probability of getting that. Sounds a bit like a combinatorics problem. And maybe you can solve it like a combinatorics problem, but there is a much easier way, I think, which is to use DP. So you can write a quadratic DP to this problem, which is gonna be something like, if we answer the last M questions, what is the probability of getting exactly Q of them correctly? And this function you can calculate based on the previous values, and it's a quite standard quadratic DP. There aren't really any tricks here. You might need to be a bit efficient with how you write this. If you write it top down with like recursion and map lookups or something like that, it might get time limit. I think the time limit on this ended up being just 1 second. So you will have to be a little bit careful here. Preferably write it bottom up with just 2 for loops. That's what I would recommend. Okay, so that was problem G. And now we move into the more difficult half of the problem set. I think problem G was like in the middle between the easy problems and the hard problems. Now we are transitioning to the harder problems. And first we have problem B, which I am surprised to see this early. I thought it was going to be harder, but a lot of people solved it. So problem B can be solved in many different ways, but some of them are quite difficult. But there are also easy ways of solving it, but I think those ways are harder to discover, but it looks like a lot of people did. So let's see first some initial observations that you will need regardless of what approach you have. So first, when is the answer impossible? When is it not possible to pick all the berries? You can see from the samples or from just drawing on the paper that if the tree is a star, then you can't do it. Because at some point you will have to pick the berry in the middle of the star, and when that happens, all the ants will run there, and you have lost. So if the tree is a star, you have just lost. You should just print no. If the tree is not a star, it turns out that it's always possible. So now we're gonna find a way of doing it. And here we have another initial observations. We can kind of focus on 2 neighboring ants. If the ants are to stay separated, there will always be 2 neighboring ants that stay separated. And it's a good idea to start by just focusing on 2 neighboring ants and ignore all the other ants. All the other ants are just an unnecessary complication to think about. So just focus on 2 ants. And here, from this point onwards, there are several ways of solving the problem. I will present the easiest one, at least the one I think is the easiest. And it goes something like this. First, pick 2 neighboring vertices, none of which are leaves. You can always do this if the tree is not a star. You can always find 2 neighbors who are not leaves, any of them. So let's do that first. Now pick a berry at one of those. Now all of the ants will run, but both U and V will still have ants in them. They can't be empty of ants at this point. And next, take a neighbor of V that is not U. So W is a neighbor. W can be a leaf if you want, it doesn't matter. And now you pick the berry at W. And what happens now is that there will be ants on both V and W, but there are no berries on V and W. We have picked them already. And this is a really good situation to be in, it turns out. When you are in this situation, however you ended up there, you can always solve the problem from here. You can take the remaining berries and pick them either in DFS or BFS order, it doesn't matter, it will work. So this is I think this is the easiest way of doing it, but some of the judges did not see this solution and instead had more complicated centroid-based solutions. Oh, here's a visualization. So here are U and V, the 2 non-leaves that we picked. So what we do is we pick the berry at V and then we pick the berry at W. And what happens is that there are ants on V and W, and we have the berries remaining. So now you can pick these red berries in DFS or BFS order, and the ants, those 2 ants that were on V and W will just run around in the tree, and they will never go to the same vertex. So that's the idea. Those 2 ants will just run around, and that's great for us. So this takes linear time, and as I said, some of the judges found the centroid-based solutions, which is you find the centroid of the tree, and you pick berries from the subtrees, and you alternate so that you don't pick the same subtree twice. And by doing this, you can make sure that 2 ants just run back and forth along the centroid, but it's more tricky to get this to work. But I saw some teams going for this approach as well. So that was problem B. It was solved pretty early, already after 34 minutes, and I think this contributed to it being solved so much, because people saw that it wasn't so hard after all, and maybe found this easier way of doing it. So it got 26 accepted before the freeze. So that was B. Next problem is problem J. So problem J, it's called the Junk Journey. It's about a robot pushing scooters into a scooter depot. So you are on a grid and you should push a bunch of items into a cell where they disappear. So in problem J, the first thing to notice is that you can use 100,000 moves, and that is a lot of moves. That is way more moves than you need. You only have like 50 scooters, and the coordinates are also small, so you can do this with a lot fewer moves than this. And so this is actually most of all an implementation problem. You just have to find some way of doing it. Okay, you can't do it like exponentially, like exponential number of moves, trying all possibilities. You can't do that, but you have to do just something that works and is reasonable. And yeah, you just have to pick like one way that is not too difficult to implement. And there are a few different strategies that all have their pros and cons, and I'm gonna present 3 of them. So the first strategy, which I think is the easiest, is what I call scooter chasing. So this strategy relies on taking one scooter at a time and kind of ignoring the other scooters and just trying to get this one scooter into the depot. So I think this is a bit easier because the logic isn't that difficult. However, while you are pushing this scooter into the depot, you will still push the other scooters as well. So you're going to have to simulate the whole thing. You're going to have to simulate all of the movements. So implementing it is still a bit difficult, but the logic isn't too hard. So this will use only a few thousand moves, nowhere near the limit, so you're going to be fine. So that's the first strategy. Next strategy. So the next strategy is that you don't even need to know where the scooters are. You can just find a sequence of moves that works regardless of where the scooters are. And you can just print the number of moves, or like the sequence of moves. So here I have a beautiful visualization of one possible way of doing this. So you can first start by like moving outside of the starting area to make sure that you are outside where there are no scooters. Then you can kind of go through the scooter area column by column and push every scooter down to below the depot. And when you know that all scooters are below the depot, you can kind of push them into the depot one column at a time. So this is, as you can see, this is a bit complicated to find this sequence, but once you have found it, implementing it is just printing all of this. So you can do almost all of this work on paper while your teammate is coding something else. And then you can just print all the moves. So that's why this strategy is actually not too bad to use. And I saw some teams who solved the problem like this. So maybe not exactly this way described in the picture, but something like where the robot is blind and you don't have to simulate. So you don't have to simulate the movement, you just print all of the moves. So that's strategy 2. Strategy 3 is, I don't think anyone actually did this, but you can also do it with kind of a Monte Carlo approach, where you try a bunch of random move combinations, and you have some scoring function, and you pick the combination that got the best score. And this is actually not as dumb as it sounds. I mean, you can take like the sum of distances of all scooters to the depot. And this is a monovariant. You want this to decrease the sum of distances to the depot. So that's a good scoring function. When this gets 0, that means that you're done. And now you just have to make sure that the scooter doesn't walk around randomly when it's far away from the scooters. So you have to just make sure that the robot doesn't get stuck for some reason because your scoring function was bad. So it is a bit tricky to get this to work, but not as hard as you would think. But I didn't see anyone going for this, but it's possible anyway. So that was problem J. It was first solved after 1.5 hours, and it got 18 accepted before the freeze. Next problem. Oh, we are at problem F. Okay, problem F is a string problem. You're given a bunch of strings, or you're given all of the pairwise concatenations of a bunch of strings, and you should recover the strings. So in this problem, there is one important trick, which is rather than looking at the strings, you should look at the length of the strings. So since you know all of the concatenations, then you also know all of the pairwise sums of length. So to figure out these lengths, you basically have a bunch of linear equations. You have a really big linear system of equations that you should solve. You don't have to use any fancy methods for solving it because it's a very special system of equations. You can add up all of the lengths in the input and figure out the total sum of lengths from doing that. And you can add up all of the lengths in one row to get, okay, so now the length of the ith string will be counted a bunch of times. And you will also count the total sum of lengths. And you can see that if n is bigger than 2, this allows you to get the length of any string. You can solve for the length of any string by doing this. And this is very helpful because if you know the length of every string, it's pretty easy to find the actual strings. I mean, you have all the concatenations. So I mean, if you just look at one row in the input, you know, like the first li characters will be string si, and so on. So at this point, it's quite easy. But okay, you still have to be careful. Once you've found all the strings, you need to make sure that it actually is consistent with the input. So that's something that's very easy to forget. And it's also easy to get like array out of bounds if strings get negative lengths and stuff like that. If the lengths are negative, I mean, you should print impossible then, but that's something you have to take care of. So that's the solution. Well, okay, it's the solution if n is bigger than 2, but if n is equal to 2, how hard can it really be? I mean, n is equal to 2, you just have 2 strings. I mean, come on. So we have this new problem now. We have 2 strings, a and b, and we want to know if we can write a as s plus t and b as t plus s for some strings s and t. That's the whole problem for n equals 2. And actually, this isn't quite as easy as it sounds. This is sort of a classic string matching problem. We had a very similar problem to this in an old NCPC from 2013, I believe. So one way of doing it is to just try every way of cutting the first string into s plus t and use string hashing to check if b can now be written as t plus s. So using string hashing here, I think is very convenient. It allows us to check for string equality wherever we want, and now it's quite easy to solve it. Another way of doing it is to concatenate b with itself and check if a is a substring of this. Now you can use k and p as well if you don't like hashing for some reason. So yeah, n equals 2 is actually kind of half the solution because you need to do a bunch of string stuff. So this problem got solved after 1.5 hours as well, and it had 13 acceptance before the freeze. And the next problem is problem E, and I'm very surprised to see E this late. I thought it would be solved a lot more. So if I had known that it would cause so many problems, I would have prepared better slides for it. But I hope the slides will still be good enough. We'll see. So the problem is simply you're given a graph and you should count the number of shortest cycles. First, you might think that this sounds very well known, but when we Googled it, it didn't give any good results. So I hope that this didn't change right before the contest or anything. But yeah, I think the best strategy is still to solve it from scratch because the search results were mainly just confusing. So let's see how to solve it. First, you need to find the length of the shortest cycle. Before you can do anything, you need to know that. And this is kind of a standard problem. The easiest way of doing it is to try every starting vertex and find the shortest cycle that goes through this vertex. And this, I think, you can think of this as finding the shortest path from the vertex to itself. So it's a shortest path problem, so you can use BFS to do this. Now you might not implement it. I mean, I did it with BFS, but you might not implement it as if it was a shortest path problem quite, but that's kind of what it is. So you do a BFS to find the shortest path from every vertex to itself. You take the minimum of this. That's the shortest cycle. So once you've done that, we want to count the number of shortest cycles. To do that, we will once again pick every starting vertex and count the number of shortest cycles going through it. We will do BFS again. And here we get 2 cases whether or not k is even. If k is even, then a cycle of even length, you can think of it as 2 paths of length k divided by 2. So you should find all the vertices of distance k divided by 2 from V, and you count the number of pairs of shortest paths to it. This is not too difficult to do because since we know that the shortest cycle is length k, there can't be any weird, like the shortest path DAG can't have a bunch of, it will basically be a tree. The shortest path DAG will be a tree up until we reach these vertices with distance k over 2. And So counting the number of shortest paths isn't too difficult. And if k is odd, it's slightly different, but it's a similar case. You once again pick the vertices that are at distance k divided by 2, rounded down. And now you want to make sure that there is an edge going between two such vertices. You want to count the number of such edges. That will be the number of cycles. And then, well, now you've counted like the number of shortest cycles going through every vertex. You probably need to divide the answer by 2 or by k or something at the end of this. Maybe divide it by 2k if you double counted stuff. So double counting, it depends on how you implemented it. Sometimes you could double count, or maybe you didn't. I don't know. It depends on how you did it. So these are all the slides I can give you at the moment. Maybe I should have made a picture or something, but there is no picture. So yeah, that's problem E. And so I saw a lot of people having time limit trouble with this. We do have Python solutions for this, actually. We don't have Python solutions for all problems, but this is one that we have Python solutions for. So if you use Python and got TLE, you can't blame Python for that. Or you can blame Python a little bit, but it's definitely solvable in Python. So that was E. Next problem is I, icy itinerary. So problem I was the second hardest. And problem I should look hard when you first look at it, because it asks you to find a Hamiltonian path in a graph, which is NP-complete. But you can also use non-edges. You don't only have to use edges in the graph. You can jump between vertices that are not connected by an edge as well. However, you can only switch between doing this at most once. So that's the problem, and the solution is you start with vertex 1, and we will simply insert the other vertices into the path one at a time. And it doesn't matter in what order you pick the other vertices, you can pick whatever order you want. And now the main trick is that if you have a partial path that is valid, it only switches at most once. There is always somewhere you can insert another node into this that still makes it valid. So you just do that over and over. So the way to do this is, if you have a partially built path that only uses edges of one color, or you can think of it that only uses edges or only uses non-edges, then of course you can always insert this new vertex at the end, and it will always work after that. Otherwise, you will have a path that uses first edges and then non-edges, or first uses non-edges and then edges. And when that happens, you should look at the middle element, the element where it switches. And let's see what we should do then. So what we should do then is, we have a picture here. Here we have our new vertex that we want to insert, and we have this middle vertex that is just where the color swaps from edges to non-edges, or the other way around. And you can see that, let's say that the edge that goes between the new one we want to insert and the middle one, let's say that it's blue. In that case, we can always insert a new one between mid and the one to the left, because now the path will still stay valid. I mean, it could be that the color between new and the left one, it could be red, and then new will become the next middle one. It could also be blue, in which case the left one will become the new mid. So both of these things can happen. You can also have that all the red edges disappear after a while, and you only have blue ones for a while, and then some red edge shows up again. And it can happen like that a bunch of times. But you can always insert new to the left here. So yeah, that's basically the solution. You just insert them over and over like this. And so one thing to note is that n is quite big. You can't do this in quadratic time. You have to do it faster. So you need to be a little bit careful with what data structures you use. You can use like a linked list here. keep a variable that keeps track of where mid is. So you need to be a bit careful, but it's not that difficult once you see the solution. But before you see it, it looks difficult. So yeah, that's problem I. And the last problem, problem K. Problem K, you are given an unknown string S, and you are given queries of two types. Either you are given the information that a substring is a palindrome, or you should answer if two substrings are the same. So this problem is really a big combination of difficult but standard techniques that you need to apply in the right way. So there are a lot of steps to this. So in what end we can start by just asking ourselves how to even check if two substrings are equal. Even if we know the string, how do we even do that? I mean, we can't just loop through them and check that all the characters are the same. That would take too long. So for this, we will use string hashing. We will store the prefix sums of the hashes, and we can get the hash of a substring in constant time. And this is very helpful. It will allow us to compare strings in constant time. However, we will also need to update this string as we get new information, so we can't use prefix sums. We will use a segment tree instead, so we can update these hash values. Okay. And what more? Oh yeah, when we get the palindrome query, we will learn that a bunch of characters are actually equal. So it's kind of like we draw an edge between them and say, these two are equal now. They are in the same connected component. They should have the same character. But how do we keep track of these connected components? Well, we will use a union find data structure to keep track of them. And so we'll need to change the corresponding entries in the segment tree when merging two such components. We will take the smaller components and only change those. This way, every element will only get updated as most log times. So that's quite good. This is most of the ingredients we need. Let's have a small visualization here. So yeah, first we will just say that all of the vertices are in their own connected component. All of the characters can be different. We don't know what they are. Where we get a palindrome query, we learn that some elements are the same in this kind of symmetric way. So in this case, we will join up these connected components in our union find, and we will change the corresponding hash values in the segment tree. So yeah, that's the idea, but there is one problem. We don't have time to go through all of these edges in all of these palindrome queries. There are way too many of them. We need to somehow skip a bunch of them. And the point is that we only care when a merge happens in the union find. When two characters are merged, even though they are already the same, we don't care. We don't even want to do it. So we can actually binary search to keep jumping to the point where merges happen, and you can use your segment tree inside of this binary search to find whether there is a merge that happens here or not. So it's a bit tricky to implement, but I think these slides should contain all of the main ingredients of doing it. So yeah, when you merge connected components with union find, I mean, you will get a tree in the end. So there will only be at most n-1 total number of such merges. So yeah, and then you might get time limit or not, I don't know, but there are some optimizations. When we get a query of type 2, I think I meant type 1 here, but when you get a palindrome query, you can start by checking if it's already a palindrome, and then you don't have to do anything. This will save you like a log factor somewhere, or maybe a factor 2 since Q is big but N is small. This is quite useful to do. And there are a bunch of such small optimizations to speed up your code. And the complexity ends up being n log squared n plus q log n. So the log squared is only in front of n, which is good because q is bigger than n. And this was solved after 2 hours and 11 minutes, and it only had 2 accepted before the freeze. So that was all of the problems, all of the solutions. Maybe we should... it will be a few minutes before the scoreboard reveal happens. Maybe we should take time to... Hello, hello, hello. Are we live? Okay, it's time to go through the results. So as you can see, it will be exciting to see who won. I think, oh, maybe not that exciting, but it will be exciting to see who comes in second place. So, but first we will start from the bottom of the scoreboard. So this is what the scoreboard looked like before the freeze. All of the yellow boxes are problems where teams have submitted after the freeze, so we don't know if they were accepted or not. So quite a lot of teams.
Oh.
So let's go through all of these frozen submissions. Let's start. So there are first some teams who didn't submit, and then Ylikumenund got accepted in the last hour and move up. Let's see how much they move up. And here we have a lot of submission-less teams. Another Taltech, and they also got one in the last hour. That's good to see. Maybe everyone should cheer when an accepted happens and say "oh" when a wrong answer happens. That's common. And now it's time for Print R again. They got accepted. Usha Fighter, Magic JMP, Rick, JavaScript Junta, Storm Coders, Kachakayo Bent. They got the accepted. Void, Vilnius Tech, Findus, Vilnius Tech 9, Stack Overflow Exception, HTTP 418. Placing last, blazingly fast. We're not last. We are in 184. False, double A, double for loop, Rockamus Lars Z, Teknisk Fysik Umeå, Haskell or Ylekumenund are finished. Next company walk-in, Software Gore, Carrick gets accepted. Teknisk Fysik are finished. NCPC, Kachakayo Bent, JavaScript Junta, Opera, Smelly Spaghetti, a smiley face with a nose. The Estonian Yard are done. Avocado are done. Team name team Norse Code. 3 coders walk into 42. Get accepted. Java Python Masters, Vilnius Tech again. Praise the Sun. Team Segmentation Fault gets accepted. ETU, Unexpected EOF. NCPC. Vitene. Informants, Chokers. Unfortunately, they didn't get accepted at the end. The lesser known, The Boys. Google Strikes Back, Tapeworm. Clueless, N to the N. The Nerd. 2 guys, 1 laptop. Oh, Exponential. Team Mailbox. So quite a lot of teams, but we are getting through them quickly. I don't have time to say all of the team names. But keep cheering and saying "oh" because that's the most important part.
Yay!
Oh, now something special happened. VGTU, Vetter, and I were the first to solve problem D. So they first found the R1 and coded it quickly. So congratulations. And we are at the top 100. Vina higher at place 100. A star is born. They are done. Random string of characters. Minimum score to pass. Advances to place 94. Netcompany walk-in 8. P minus minus. Gecko kickers. And P pojkar. ATU number 2. Halt and catch fire. IT boys. A lot of teams who are finished now. Team name Amper lovers. Blue Jay wizards. DP question mark. We are just here for the balloons. They got one more balloon. Pythons. Segfault syntax error. No country for old men. Vilnius Tech 1. Naxi trolls. Fibbers. Bobby tables. It's one accepted. Python pirates. CPP the reference. Didn't get anything in the last hour. Funky Functors are finished. Netcompany walk-in 7 gets one more accepted. F++. And here we have a lot of finished teams. 5 Euro engineers. And retired gets one accepted. Bobby tables is done. O of square root of -1 didn't get anything in the end. Hex Street Boys. Econ 101. Ash lads. We're just here for the balloons. NCPC senior initiative. Algorithms and data drummers. Placeholder done. ON factorial. Yeah, ICP C++ solves problem B in the end. Good job solving that one. KTU number 1 get one accepted at the end. They implemented the grid problem there at the end. The Plorit made of Java gets the berry battle at the end as well. The simulators, Artul, F Langastrik, Dal Doma. A lot of attempts on problem F there. Kungliga Kodare had a very big number of submissions. P-Space Invaders, Netcompany, Econ 101, retired. Scream and See Out gets an accepted at the end and advances in the top 20. Lord of the Graphs, Fatal Error gets an accepted and they also go into the top 20. Lords made of Java are finished. F Slangastrik. Now the resolver stops because F Slangastrik are the Icelandic champions. In place 32. Next up is Grape, who had a lot of submissions at the end, and they got one of them at least. Hope it passes. It didn't pass. Maxmin Age, they got problem I at the end. Oof. Coming soon is problem E. Nick. Oh no, we didn't get J there. Binary Polos, Daimi Old Boys, a lot of submissions from Daimi Old Boys. Maybe they have even more up their sleeves at the end. Tiki Pelli, Skalgo Man also gets an accepted. Team O of LD. No more accepteds. Rainbow Unicorn characters. Yeah. And Scream and See Out are finished at place 26. A lot of Danish teams here. Maxmin Age. They are also finished after a lot of submissions there. Binary Polot didn't get I or J. Tiki Pelli, Daimi Old Boys, even more submissions from them. Maybe I. Oh, they got I as well at the end. A lot of work was being done the last hour there. Raspberry Jam got problem B. Noobs at LTH got problem F at the last minute, I think. That's impressive. Amazing from DTU are finished. Rainbow Unicorn characters got one more the last hour. Oh, This team didn't get anything in the last hour. Last Laget from Chalmers got B. Roger Kribben got E. Coming soon, didn't submit. Yeah, they got one in the last hour, yeah. Eitoloxel Valley Kuha Voita are finished. Noobs at LTH, Raspberry Jam. Oh, they got problem F there 2 minutes before the end. And Rainbow Unicode characters got another one as well in the last hour. A lot of submissions in the last hour that ended up working. PSE didn't get one though, but PSE, they are the first something, I don't know. Oh, so first solver on problem A. So they dared to go for A first. EZCP, a lot of names along that line this time around. They got the problem, they got accepted. Rainbow Unicorn characters are in 10th place. Last Laget in 9th. EZCP are in place 8, and they were also the first to solve problem, I believe that's F. So, Cyan Forces utan xylofon. They are in 7th place, so good job. They are the Sweden champions actually. And now we are soon in top 5, but first Bubblegum Bitset. They didn't get I at the end, but they are still the Estonia champions. And now it's this string of characters are currently in 5th place, but they advanced to 3rd place. The Kexi fan club. Will he get K at the end? They did get K at the end. Okay, the good Minima, the one-man team from Norway in 5th place. And they are also the first to solve both C and J. So very impressive performance there from the good Minima. And in 4th place we have this string of characters from University of Bergen. And they were the first to solve problem I. And are they also Norwegian champions? They are the Norwegian champions. Okay, we are now in the top 3, and it's very exciting to see who ends up in 2nd place here. We have Define True Rand, and they get problem I at the end and get into 2nd place. And 3rd place we have Kexi Fan Club, who are the first to solve problem H, and they are also the Finnish champions. And in 2nd place we have Define True Rand, first to solve problem K, and Lithuania champions. And finally, the Balloon Animals, who solved everything before the freeze, are the Danish champions and solved B, E, and G first. Congratulations, Balloon Animals, the NCPC 2022 champions. So, 2 teams that solved everything, 2 teams at 10. A lot of solved problems this year. This was, yeah, that was all. Hope you had fun. Thanks for coming.